All right, let's define work further. Remember, previously we had talked about work as force acting on a distance. I want to further define that by talking about what's called PV work, where P and V is pressure times volume. So PV work. In order to do this, I would like you to visualize something. Let's consider a chemical reaction in a capped beaker. Okay, so here is our beaker, and what I'm going to do is I'm going to put the cap down here. Okay, so here's my cap here. And underneath this cap, I'm going to have my reactants. Now, I want you to imagine that as this reaction proceeds, those reactants start to produce a gas. So as the reactants become products, they start to produce a gas, and the gas moves the cap upward. Okay, the gas, as it's produced, it pushes the cap upward. So here's the gas. Okay, volume of gas that's generated here. So we could measure the difference or the distance which the cap has been pushed up in this cylindrical beaker and the volume of that beaker that the cap has moved up would be the delta V associated with this change, okay? So like any system, like any chemical system, the reactants are our initial state here and the products are our final state. So we can see that in going from the initial state to the final state, we have had an increase in the volume of the system. Now, the system is your reactants, right? And I think that it's not too much to ask you to imagine that the system is doing work to raise that cap. Okay, so the system does work on the surroundings to raise this cap inside the beaker. Now, we do sign conventions with work from the point of view of the system. So this means that the work, W, will have a negative sign because when we talk about the system doing work on the surroundings, we assign that a negative sign. So we can think about that work as being W equals negative P delta V. The change in the volume of the system is kind of like the distance, and the pressure here that the system is exerting on the cap is kind of like the force. So this is kind of the same idea as force times distance, but it's pressure times the change in volume. So our work here is equal to minus P delta V. And the work has a negative sign because the system is doing work to raise that cap. Now, we tend to measure pressure in atmospheres and we tend to measure volume in liters. So the units here are going to be liter atmospheres, because volume is measured in liters and pressure is measured in atmospheres. And you guys may sometimes need a conversion factor. 1 liter atmosphere is equal to 101.3 joules. So you can interconvert. Those are both units of energy. A liter atmosphere and a joule, these are both different units of energy, and you can interconvert between them using that conversion factor. Okay, so this idea of PV work leads us to the next big thermodynamic state function, which is enthalpy. Enthalpy is an extremely important state function. We denote it with a big capital letter H. It's a state function. And sometimes we call it heat. That's where the H comes from. Heat is kind of synonymous with enthalpy. You can visualize enthalpy as the heat content of molecules. So if you think about molecules are just atoms that are bonded together and those bonds contain energy. So imagine enthalpy as the heat content of molecules. Um, I'll write that down, in fact, enthalpy, heat content of molecules. So we have chemical energy stored in molecules. Another way you can define enthalpy is as the internal energy of a system plus the product of its volume and pressure. Now, you've seen the product of volume and pressure before. That sounds a lot like PV work. So enthalpy H is equal to the internal energy plus the product of the volume and pressure, PV. So I just kind of wrote down that definition. Let's put a delta in front of everything here so we can think about the change in enthalpy. It's a thermodynamic state function, so we can really only measure the changes. So we have delta H equals delta E plus delta PV. All right, so we've seen some of these things before. From the first law of thermodynamics, we know that delta E equals Q plus W. And delta PV is something that we've seen before a moment ago when we've defined PV work. So I want you to imagine for a second that we are talking about a system at constant pressure. Most chemical systems are at constant pressure, so this is not very far-fetched. If we are talking about a system at constant pressure, then we can pull that P out from under the delta because pressure is going to be constant. So I can call this P delta V. Delta H equals Q plus W plus P delta V at constant pressure. Now, W, we just defined. It's PV work. So W equals negative P delta V, right? Remember from just a moment ago, we talked about how W equals minus P delta V. So I can plug that into my equation here. And now look what happens. Minus P delta V plus P delta V, this boils down simply to Q. So what I have just done is determine that at constant pressure, enthalpy is just equal to heat flow. Delta H equals Q. Sometimes you'll see a little subscript P here to indicate that we're talking about constant pressure. So another way of defining it is that enthalpy is equal to heat flow. Remember, Q is heat flow, path function, at constant pressure. So that is a useful definition of enthalpy. The change in enthalpy of a system. Okay, so if I want to be really correct, I need to say the change in enthalpy is heat flow at constant pressure. The change in enthalpy of a system is heat flow at constant pressure. And enthalpy is a capital letter state function. So that means that, we're looking at delta H. And for a chemical reaction, the delta H of a reaction, we can take the final state, which is just the products, the enthalpy of the products, and subtract the enthalpy of the initial state, which is just the reactants. And that's how we can tell how heat is flowing in a chemical reaction. So enthalpy gives us the energy flow of a chemical reaction in the form of heat. So we can see whether heat is flowing into or out of a reaction. And that is something that is pretty easy to measure using a technique called calorimetry. So some sign conventions here. If delta H is negative, from the point of view of the system is the reaction. The reaction is exothermic. So this is a sign convention. If delta H is given a negative value, it's because the reactants are higher enthalpy than the products, right? That's what would have to happen to give us a negative delta H. So that means that heat is released by the reaction from the reaction to the surroundings. So again, the reaction is the system that we're talking about. If delta, then conversely, if delta H has a positive value, that means that the enthalpy of the products exceeds the enthalpy of the reactants, and the reaction is endothermic. That means it's going to require energy input in order to proceed. Okay, so an endothermic reaction requires heat input in order to be able to go in the forward direction.